Welcome. This video is going to take a look at a special group of ionic crystals that are called hydrates. Water molecules can adhere to ions as the solid forms or even after the solid forms. At any rate, the water becomes trapped and is part of the crystal. Opals, other gems are common hydrates and they get their color from the water. Hydrates are often used as desiccants, those little packages of crystals that come in your shoebox and other things. Or most often, people are familiar with it from disposable diapers. So hydrates have a specific amount of water associated with each formula unit. Or in other words, each crystal, if you had it in its simplest form, each formula unit can hold a certain number of water molecules. And it could be just one molecule held by the crystal per formula unit, or it could be many, 7, 12. Obviously, disposable diapers can hold a lot. That's what makes them so good, is that a very small amount of crystal can hold a large amount of water. So the amount of water each crystal can hold is indicated in its formula. So you see here there's a formula for sodium carbonate, Na2CO3, and then it says 10H2O. And the 10H2O is deliberately set apart. There's that little times sign or dot between it because it's not actually a chemical reaction. Absorbing that water is just like when a crystal dissolves in water. It's just a physical change because you can dry it back out, get the water back out of there. So the H2O is listed separately or after the formula. And then the 10 indicates there's 10 moles of water for every mole of the ionic compound, or 10 molecules of water is absorbed by each formula unit. So an Na2CO3 formula unit can hold 10 molecules of water or trap 10 molecules of water in there. So the water must be calculated into the molar mass of the substance when it's hydrated. And the name is also indicating it's a hydrate. If it was just the crystal dried out, we'd call it sodium carbonate. But because it's fully hydrated, it becomes sodium carbonate decahydrate. So let's look at an example of both naming and finding the formula. So finding the formula, you need to know the number of moles of water and compare it to the moles of the hydrate. So in the lab, what you would do is mass the hydrate. That means when the crystal is full of water. And then you heat the hydrate until you evaporate all the water. Okay, until you drive all the water off and you have just the crystal left. And then we call that the anhydrous compound, the crystal with no water left in it. You can use the difference in mass between the hydrate and the anhydrous to determine the mass of the water, and then you can change that to moles of water. So a couple terms you need to keep in mind is that hydrate is referring to the crystal with water in it, and we're going to assume it's absorbed the maximum amount of water. And the anhydrous is referring to the crystal or just the ionic compound itself. So let's look at naming. You write the name of the ionic crystal without including the water, and then you choose the correct prefix for the moles of water that the hydrate can hold, such as mono, di, tri, tetra. Then remember you get to the easy ones, penta, hexa, hepta. And then you use the prefix with the word hydrate after the ionic crystal's name. So for example, zinc 2 sulfate combines in a 1:7 molar ratio with water, or in other words, forms a hydrate that can hold 7 molecules of water per formula unit. So to name this crystal, I would just write the name of the ionic crystal without water in it, so zinc 2 sulfate. And then the prefix for 7 is hepta. And I attach the word hydrate to it. So zinc sulfate with 7 molecules of water. Finding the formula for the hydrate's a little more work, but it's very similar to what we've been doing with empirical formulas and molecular formulas. You subtract the mass of the anhydrous crystal from the mass of the hydrated crystal, and when you're working problem sets, both these masses will be given to you. It'll probably be based off of some experimental data. And when you do it in the lab, your anhydrous crystal will be what you're left with afterwards. The hydrated crystal is what you're going to start with and dry out. You convert the mass of water to moles of water, and then you also convert the mass of the crystal only, or the anhydrous crystal, into moles. You then divide the moles of water by the moles of compound. Remember, the moles of water can be greater than the moles of the compound. But the moles of compound should never be greater than the moles of water, because the compound can hold one or more molecules of water. So once we have it in moles, moles of water should be equal to or greater than the compound. And when you divide, you should get a whole number or within a few 1/100ths that you can round it off. You shouldn't be getting any fractions here. And so then once you have these molar amounts, you go ahead and write the final formula. Let me show you an example of how this is really a combination of what we've been doing with empirical and molecular formulas. You have 5-gram sample of a hydrate of barium chloride. After heating, the dried barium chloride has a mass of 4.26 grams. What is the formula and name for this hydrate? So I have 5 grams of the hydrate, so that's the water plus the crystal. And barium chloride, barium has a +2 charge it picks up, and chlorine just a -1, so this is water plus BaCl2. 4.26 is after, so that's my anhydrous crystal, or just BaCl2 only. That means if I subtract these, the difference, 0.74 grams, should be my water only. So now I know the mass of my barium chloride and the mass of my water, so I can convert each one to moles. So 0.74 grams of H2O, 1 mole of water, it's got 2 hydrogen at 1.01 each, 1 oxygen at 16, so that's going to be 18.02 grams in a mole. So 0.74 is going to be a very small amount, divided by 18.02. So this is just 0.0411. It's like, wow, that seems like too tiny. Well, let's look and see how much barium chloride we have. We have 4.26 grams of barium chloride. And BaCl2 is going to have a molar mass. Barium is quite heavy at 137.33. Just one of them. Chlorine, there's 2 of them at 35.45. So this molar mass, 137.33 plus the 2 chlorine, is a molar mass of 208.23. So 1 mole of barium chloride, 208.23. So this is also going to be a very small amount, 4.26 divided by 208.23. This is only 0.0206, 0.055, we'll round it to 0.06. So now when I take my 0.0411, my moles of water, divide by my moles of crystal, I'm going to get 0.0411 divided by the 0.0206. I get 1.995, or 2. So that tells me my formula is BaCl2 with 2 H2O, and the name then would be barium chloride dihydrate. Okay, so I've got a couple examples for you to try on the next 2 slides. Gypsum is a hydrated calcium sulfate. A 5.91 gram sample of this hydrate was heated, and after the water was all driven off, 3.87 grams of anhydrous calcium sulfate remained. Determine the formula and name for the compound. So go ahead and pause and see what you can do with this one. And I'll work through my solution as well. So first thing I need to know is a formula for calcium sulfate. Calcium picks up a +2 charge. Sulfate's SO4 and picks up a -2. So the formula for this is CaSO4. I'm going to need the molar mass for calcium sulfate. So I see that 1 calcium weighs 40.08 grams. 1 sulfur weighs 32.07 grams. And the 4 oxygen weighs 16 each. So my molar mass for calcium sulfate, 40.08 plus the 32.07 plus the 4 oxygen gives me a molar mass of 136.15 grams per mole. And H2O, when you work a few hydrate problems, you remember this fairly quickly, that there's two hydrogen, 1 oxygen, or molar mass of 18.02 grams per mole. So if I look at my data, I've got 5.91 is the before. So this is my CaSO4 with water. Afterwards, it's just 3.87. So this is my CaSO4 only. And when I subtract these, 1.04 is my water. So the 3.87 grams of calcium sulfate can be changed to moles by 1 mole with a mass of 136.15 grams. So 3.87 divided by 136.15 is 0.0284 moles of calcium sulfate. The water had a mass of 1.04 and can be converted with the equality that 18.02 grams in a mole of water. So 1.04 divided by 18.04 gives me 0.0576. So now that I have my 2 molar amounts, I need to go ahead and compare them. So 0.0576, the water's got more moles than the crystal. It looks to be about twice as much, but I'll divide to be sure. 0.0576 divided by 0.0284. And I come up with 2.028. So it's 2 times, or 2 molecules. And so my formula would be CaSO4 with 2H2O, or calcium sulfate dihydrate.